Okay, welcome everyone who's online or about to join us. The topic this week has been galaxies. We're moving out in the universe. Only 2 more topics and weeks to go. So I welcome your questions on the larger universe.
Okay, so on Udemy, Kent asks, last week, Super CDMS reported 3 possible dark matter candidates. Do you have a comment?
Yes, it's a very exciting experiment. This is breaking news. Dark matter, as you know, is majority component of the universe. Let's set aside dark energy for a minute. But dark matter outweighs normal matter, which is called baryonic material, protons, electrons, neutrons, by a factor of 6 in the universe on every scale. And we don't know what it is yet. We've ruled some things out, but almost the only possibility remaining is a fundamental subatomic particle. So the CDMS experiment that was being referred to in the question is a physics experiment to detect dark matter, because astronomers can diagnose its existence, but they really can't say what kind of physical entity it is from astronomical observations. So the CDMS experiment reported 3 events, particle interactions essentially in their detector, and that's tantalizing, but it's really only just tantalizing. And I think the CDMS experiment, the group were very cautious in their language, but of course they want to draw attention to their experiment. What they saw was 3 particle events consistent with a particle that has the properties of dark matter, which is to say that it's a particle with very weak interactions with other matter, essentially no electromagnetic interactions, really manifesting its presence only by gravity. As an aside, detecting a particle like that is quite difficult. Particles that are charged or have clear and strong electromagnetic interactions are much easier to detect. We can make them interact with light or emit light or absorb light or move in a magnetic field. Lots of ways we can detect such particles. A dark matter particle with weak interactions with the electromagnetic force is very challenging. In fact, the best way to detect such particles is by mechanical resonance, is literally by the particles colliding in the lattice or material of a detector and us detecting that collision energy. So 3 events, what does that mean? Well, they were also careful to say in the experiment that their background, because there are random, unrelated particle interactions in any detector that constitute a background, or noise if you like, something that confuses you from the signal you're trying to measure. Their background was 0.7 events. Now that doesn't mean that the 0.7 of an event doesn't sound very meaningful. That just means the statistical average in any period of time or volume of the detector was 0.7 for this reference. And so they detected 3 events where they would have statistically expected to find 0.7 events just from random unrelated processes. That's the basic result. Now why is that not something you can just go home, go to the bank with, or warm up a Nobel Prize for? And I'm not being facetious. The discovery of dark matter in a physics experiment might well generate a Nobel Prize for the team leader, and probably in short time, probably within a couple of years. The answer is statistics. The odds of getting 3 events where a half or 0.7 were expected are not incredibly low. They're more than 1%. In other words, this result has a significant probability of being spurious. And astronomers and physicists, of course, use a high bar on statistics. You've heard of the 3 sigma, 5 sigma, and so on. That essentially relates to the probability that a result is not due to random statistical noise. Well, the CDMS result is a 3 sigma detection. And better than 99%, but not much better. Now, 1% chance of being wrong doesn't sound like much, but it's not enough to make the physicists comfortable. The Higgs particle, to rewind to a big physics result of the last few years, after their first run of data, they had a 3 sigma detection of the Higgs, but they didn't make an announcement. They actually sat on it for another whole year until they could gather more data with the Large Hadron Collider. And the Higgs result was only announced when it was 5 or 6 sigma, twice the significance level, which actually means a much, much lower probability of being spurious. So basically, it's just too early days for this experiment. They need to gather more data. It's tantalizing, but it's not a strong enough result for them to be very confident that it's real. If it is real, however, and it does pan out, it'll be one of the discoveries of the decade, if not of the half century, since we've been looking for dark matter for about that long.
Carol's wondering, can you tell us a bit about the evolution of blue giants? Do they swell up and develop a surrounding shell structure like red supergiants? And what are the main differences between red and blue supergiants?
Red and blue supergiants, or really any supergiant star, is a very high mass star. So these are the states of stars where the main sequence lifetime, or the lifetime on fusing hydrogen into helium, as the sun is doing, are very short, times of maybe a few million, maybe 10 million, 15 million years. So far, far shorter, orders of magnitude shorter than the sun's lifetime doing that fusion event. The distinction between, remember that stars essentially bifurcate in their properties late in their evolutionary histories. What happens all through a star's life is a tussle between the implacable force of gravity pulling inwards, trying to create higher temperatures and more pressure, and the pressure itself, which is caused by energy released from nuclear reactions. That's the battle between an inward and an outward force that governs a star's life, and any given state of its evolution is the balance between those forces. Late in a star's life, when it's moved to very high temperature states and advanced fusion reactions, much higher than helium, even into carbon, but probably things like creation of silicon and even the iron. It's the slag heap at the center of all massive stars. The red and the blue supergiants reflect what's going on in the atmosphere of the star. It's rather decoupled from what's going on in the fusion core. The blue supergiants just have a larger energy transmission into their outer envelopes, which keeps the envelopes hotter. And in fact, those envelopes are actually physically smaller than the red supergiants. The red supergiants have had energy deposition from the nuclear core that's essentially blown up, like inflating a balloon, the atmosphere of the star to a very large size, hence supergiant, and also a very cool temperature. And that's why they're red, because their thermal temperature is something like 3,000 or 4,000 Kelvin, making them red stars. So the distinctions between red and blue supergiants are actually just due to the subtleties of the nuclear reactions and how they transmit energy into the envelope of the star. Both types of stars are doing advanced fusion reactions leading towards the heaviest elements. And they're both typically massive stars, maybe 8 to 10 or more times the mass of the sun.
Okay, Phil asks via email, would there be any impact to life on Earth if our galaxy had an AGN?
Yeah, interesting question. To spell out the acronym, AGN is the acronym for active galactic nucleus, or active galactic nuclei. And in the larger universe, AGN are intensely bright objects in the sky because they have extraordinary activity near a supermassive black hole. And so these are basically objects like a normal galaxy, where somewhere in the center is something the size of a large city that is emitting, could be hundreds of times more light than the entire galaxy in non-thermal radiation, coming all the way from radio to gamma ray wavelengths sometimes. That's an extraordinary situation. Our galaxy has a massive black hole. It's supermassive. It's 4 million solar masses. That's not as big as they get, but it's pretty hefty. But it's not an active galaxy. So the question is, what would our galaxy look like if it were more active? It has the massive beast, the gravitational engine at the center, but the engine is not doing it. It's stable, actually. And we've seen evidence of that because in the interior of the galaxy, although there's a dense star cluster, there's not a lot of gas. The previous episodes of activity probably, or just massive stars dying like supernova have blown out a lot of the gas from the very central region of our galaxy, so the black hole there has nothing to eat right now, so it tends to be quiet. So let's ask the hypothetical of the question, what would happen if our galaxy went through an active phase, as we think every galaxy does, and that's how their black holes grow over time? It would be impressive. If our galaxy were to suffer an eating event or manage to get enough material near the center to go into a bright phase, as opposed to its quiet phase right now, it would brighten by many orders of magnitude. And we can imagine, like an active galaxy or quasar out there at much larger distances, that the center of our galaxy would have enough light in a very small region that it rivaled the light of the entire galaxy. And if that were the case, that would be on the verge of being visible in the daytime sky. And it would very much mean that the center of our galaxy would be the brightest thing in the night sky. It's a matter of conjecture whether our galaxy could be active enough that it would literally be visible in the daytime sky, but it would be by far the brightest thing in the night sky, dominating the night sky and probably rivaling the moon in brightness, which would be an extraordinary situation. It would also be dousing us or dosing us with high energy radiation. And would that have an effect? Would that have a bad effect on us? I don't think so. That radiation is going to be diluted by traveling 27,000 light years from the center of our galaxy. And that's enough distance that we'd probably be safe.
Jerry wonders, what particle makes up a cosmic ray?
Cosmic rays are of several varieties. The phrase cosmic ray, it's a sort of historical term, an anachronistic term really, because we don't use the term ray very often, because really what they are is particles. They're definitely not rays as in waves of light. Several types of particles. Historically, the ones that were found first were actually in the atomic nuclei. Now, very often hydrogen nuclei, so very high energy protons moving at essentially the speed of light, because they're highly relativistic. But also, as people were able to analyze these high-energy particles by moving them through magnetic fields, they realized that they were also looking at alpha particles, or helium nuclei, so 2 protons and 2 neutrons, that arrive at the top of the atmosphere and sometimes penetrate through. So we see accelerated to high energy and cosmic rays, the basic stuff of the universe, which is hydrogen and helium, so protons, the nuclei, and helium nuclei. There are also very high energy or relativistic electrons, and those can be cosmic rays as well, or count as cosmic rays. But they don't, because of their much lower mass, they don't tend to penetrate as far. We detect cosmic rays somewhat indirectly, because as cosmic rays arrive at the top of the Earth's atmosphere, they of course are likely to interact with the diffuse gas in the upper atmosphere. And so what cosmic ray detectors on the Earth's surface are typically detecting is not the cosmic ray, the incident cosmic ray that arrived through deep space at the Earth's atmosphere, but a shower of secondary and tertiary particles created by interactions of that cosmic ray with particles in the Earth's atmosphere. A whole cascade of particles, essentially, that douses the detector on the ground. These are phenomenal energy particles. The highest energy cosmic rays exceed by orders of magnitude the energy of accelerators like the Large Hadron Collider. In fact, it's a terrestrial type analogy, but it's accurate. The very highest energy cosmic rays yet detected have the energy in a subatomic particle of a well-thrown fastball. That's quite a thought. So yes, if it hit you in the head, that proton, it would hurt.
So Jerry asks, could you please talk about how Cepheid variables are used to measure distance?
Cepheid variables, it's an important topic because historically it was the way that we found that the galaxies were separate systems of stars and not just fuzzy patches of star formation in our own galaxy. So it's more than just a historical aside, because Cepheid variables have been used since then to measure distances. It's essentially opportunistic. Astronomers are opportunistic in using tools that nature provides to make their measurements. When we move beyond the galaxy and try and measure distances, it's really hard to do so. In the general scheme of things in astronomy, the most direct way to measure a distance is parallax. That's actually using the motion of the Earth in its orbit of the sun to make a skinny baseline of a triangle and actually measure directly the skinny angle of that long, thin triangle. So that's pure geometry giving you a distance. But that only works out to a few hundred, maybe 1,000 light years, well within our galaxy. To go beyond the Milky Way, cepheids were the tool of choice, and they were perfected as a distance indicator, as the phrase goes, in the 1920s. The physics is that these are variable stars with rather well-regulated variability. As you recall in the material on the sun is thermostatically controlled, such that if something happened to perturb the sun, make it either a little larger and cooler or a little smaller and hotter, the nuclear reaction rates would go in the opposite direction to compensate, and so the sun would stabilize. And cepheids are also fundamentally stable objects, but they have pulsation modes. In other words, in their variations, they can go into an oscillatory phase where the envelope changes in size periodically, not in such a way as to blow the star apart, but in such a way as to regularly change its structure. It's just like a sloshing puddle of water, or almost any oscillation, except this is a star in oscillation. And it's an oscillation of its actual structure, so it's changing the fusion rate in a periodic way. The physics of the variability and this change in its physical nature is periodic in an interesting way. The period varies with the luminosity, or the intrinsic brightness of the star. So the higher luminosity variable stars have longer periods. And when astronomers started to gather cepheid samples of these variable stars from around the galaxy, they saw that this was a beautiful correlation, a linear correlation between the period and the luminosity. Actually, it's in a logarithmic scale, but it's linear. And that suggested something very interesting. That suggested that if you could find a cepheid variable somewhere in the galaxy, but you didn't know how far away it was, and you just measured the period of its variation, you could predict from this linear relationship, just like a lookup table, what its luminosity was, which means its intrinsic brightness. Knowing its intrinsic brightness and the inverse square law, you can calculate, and how bright it appears to be, you can calculate its distance. So that's an interesting and clever technique for measuring distance. You just need to find the variable star, measure its light curve, or just monitor its variations over a period of months. Weeks to months is the typical time scale. And you can get the variation and then easily get the distance. That was the method. And that's a method not invented by him, but the one that Hubble used to measure the distance to Andromeda and other galaxies. Now, in the era beyond Edwin Hubble, we've used the telescope named after him, the Hubble Space Telescope, to measure the distances to a larger set of galaxies using cepheid variables. That method has been taken to the edge of the Virgo cluster, so that's about 50 or so, maybe 60 million light years. So that's pretty impressive. And that's about the limit of how far you can use this clever technique based on variable stars to measure distance. The reason that you can't use it any further is not because the cepheids are too faint for a telescope to detect in a galaxy further away. It's really because the cepheids become confused with the stars in the galaxy. So as the galaxies get further away, the cepheids, which are intrinsically quite luminous stars, much brighter than the sun, maybe 100 times more luminous than the sun, they're visible, but in any galaxy at that large a distance, whatever patch of the sky you're looking at with this variable star also contains hundreds and hundreds of other stars that you can't resolve or separate out with your telescope, even with the Hubble Space Telescope. And so essentially you're confused. You're not looking at the light from a single star. And that's sort of the practical limitation to how far we can use cepheids to measure distances. After cepheids, just to finish the thought, we use supernovae. And those are, of course, single dying stars that at their peak brightness rival the brightness of the entire galaxy. So we essentially can use supernovae to measure distances almost as far away as we can see galaxies themselves.
Stanley asks, can you talk a bit more about the difference in relativity and special relativity that you addressed in the question about galaxies at some time in the future moving apart at a greater than speed of light?
Right, that was an important question, and I'll rephrase it for those who didn't didn't see it in the thread. It was alluding to the fact that in the expanding universe, in the standard picture of the expanding universe with the Big Bang 13.7, 13.8 billion years ago, there were times in the past, in fact, the first third of the history of the universe, the first 4 or 5 billion years after the Big Bang, where any 2 points in space were moving away from each other faster than the speed of light. And that sounds like a problem, because didn't Einstein say that the speed of light is an absolute limit? Yes, it is a problem on the face of it. The answer is that Einstein had 2 theories. The special theory of relativity, which came first, was his supposition, based on observation, that the speed of light didn't depend on the motion of the observer and was an absolute limit. And that was verified with terrestrial physics. But without getting too technical, special relativity is based on positing something called an inertial frame. That's a frame of reference where we can measure distances and times by synchronizing clocks and sending light beams around. And the entire situation, the experiment, is static. It isn't changing or moving. In such a situation, which would apply in the solar system or significant regions of the galaxy, special relativity is the way things work. Speed of light is an absolute limit. So that's special relativity. General relativity, and as you can, the words tell us something. Moving from the general theory, Einstein was generalizing his theory. He was generalizing it to situations of non-uniform motion or acceleration. So general relativity is the theory that governs the behavior of the universe. And in the general theory of relativity, there is attached to expanding space-time. Space-time could, in principle, contract or expand when you solve the equations of general relativity. In our universe, space-time expanded, and general relativity describes it very well. And in the theory, and we think in observation too, there's no speed limit assigned to the rate at which space-time can expand, carrying the galaxies away from each other as a result. And so, in the theory, if you project backwards, indeed, the early parts of the history of the universe involve superluminal, or faster-than-light expansion. And that's what the theory says, and that's what we think we can see. Special relativity is not violated because special relativity's realm of application is on much smaller scales. And so both theories can be valid, but the regime of validity of general relativity is global. It's the entire universe, and it's talking about expanding space-time. And in general relativity, there's no speed limit assigned to an expanding universe.
Okay, our next question is from Bill. He asks, since dark energy is helping to expand the universe, does it congregate near the far edges of the universe where dark matter may be sparse?
Okay, that's an interesting question. And it's an important question about what is the distribution of dark matter and dark energy. So I'll take the question and generalize it to that. What can we say about the spatial distribution of dark energy and dark matter? And to refer to the framing of the question, I would say that we have seen no sign of either dark matter or dark energy congregating in any way towards what we might call the edge of the universe. There is no center of the universe as far as we can tell because there's no privileged position. The galaxies all moving away from us is a situation that would occur if we were situated on any galaxy in the universe. We'd see the same thing. So there's no center. The edge is also a tricky concept because what we really have is an edge in time rather than an edge in space. So when we're talking about dark matter or dark energy distributed in a particular way, when we look out in space, we're not really testing that because as we look out in space, we're looking to the universe when it was in an earlier state. So really, when we look out with a big telescope, we're talking about dark matter and dark energy then, as opposed to dark energy and dark matter now in the nearby universe. That's the issue. But the question is still valid. Is there any observation astronomers have made that addresses the spatial distribution of dark energy or dark matter, or the temporal distribution? For dark matter, the answer is yes. There's tons of observations that have addressed the spatial distribution of dark matter. I just interviewed for one of our podcasts, the 3 that did news with low and Zabel works on galaxy clusters and diagnosing dark matter through that. So you'll hear about how the lensing technique is used to say some quite interesting things about dark matter and also the first galaxies in the universe when you listen to that podcast. Dark matter we now have mapped out in very many different regimes. We know that it's the halos of all galaxies are consisting of a sort of diffuse potential well of dark matter that's bigger than the visible parts of the galaxies we see and more massive by a factor of 6. And that the galaxies cluster and aggregate into groups and clusters and even superclusters, and those visible aggregations are embedded in dark matter potentials that again exceed the visible stuff by a factor of 6 and are distributed on very large scales. So we've mapped out the undulating density of dark matter in the universe. Not as well as we've counted galaxies and their locations, because it's harder to do, but you can trace the dark matter in general, and the dark matter is in general more large distributed and smoother distributed than the galaxies are. So that's consistent with our theory, which says that the dark matter is cold. And when you hear cold dark matter, that means a particle essentially that was subrelativistic back when the microwave background radiation from the Big Bang was being created 400,000 years after the Big Bang. That's sort of just a technical distinction about dark matter. So we've learned a lot about dark matter with the what it is question hopefully answered within a year. For dark energy, our ignorance is almost complete. It's really quite a discouraging situation given how important dark energy is in the universe. It's 3/4 of the universe near enough. And we know of its presence purely by the fact that the universe is accelerating. And that's just a global imprint of an accelerating rate of expansion in every direction we look. And really that's all we can say. We don't see any different imprint of dark energy looking in any direction in the telescopes. Which is reassuring because nothing else in cosmology has shown an orientation dependence. There's no sense where if you look deep in with a telescope, you see different distant galaxies or places where there are no galaxies and some where they're completely piled up. So we've been surprised that dark energy had varied depending on which direction we look. The more difficult question to answer is whether dark energy has changed its nature over cosmic time. And I think the truth is that that's a very hard experiment and the jury's out. A few people have claimed a result to show that it does not vary with time, that the absolute value of dark energy, which we think emerges from the vacuum, was the same 5 or 8 billion years ago as it is now. But those are very difficult observations, so I would not say that's been nailed down. That's a fairly long-winded answer to a simple question, but it's an important question because it alludes to some of the biggest issues in cosmology at the moment.
Gabriella wonders, could a wormhole be some kind of black hole, but without losing information?
Wormholes, yes, it's a great topic. I do recommend Kip Thorne's book, and I'm not going to remember the title in real time, but Kip Thorne is the Caltech gravitational theorist, physicist, totally top of his game. He's the chief scientific consultant or chief scientist for the LIGO experiment, which we talked about in the first week of the course. Kip Thorne's written a book, White Holes and Black Holes and Wormholes, I'm not sure in space.
Black holes and time warps.
Black holes and time warps. And I really, for the larger view on this subject, I recommend you to that book because he does something which is a little unusual for a physicist. He sort of takes off his straight-laced clothes and face, and he speculates meaningfully around the edges of his subject. And remember, he's not just some guy, you know, he's not some average physicist. He's almost top of the game as far as gravity physics goes. And he admits that we have to consider the possibility of these things, wormholes, places maybe where whatever information does apparently get lost in a black hole, since we don't know that it's preserved holographically at the event horizon. That's a hypothesis with no evidence to support it. He speculates about these ideas about the other end of a black hole being a white hole or wormholes connecting space-time. And I think he's careful in line between unwarranted speculation, and both by the theory and by the fact that we simply don't know. So the simple answer to the question is these things are possible. Our state of knowledge is just too primitive to really say whether they happen or not.
Jerry asks, what is the current thought on the end of the universe?
Well, it's a good question, and it relates to the last but one question. The current thought on the end of the universe is that in a universe where dark energy dominates, remember it in the sort of pie chart, if you like, of the universe, of what it's made of. The universe is 70 or so % dark energy, roughly a quarter dark matter, and just a few % normal matter, the stuff we're made of. The dark matter acts like a brake on the cosmic expansion, and the dark energy acts like an accelerator on the cosmic expansion. So at the moment, we have the accelerator pressed down 3 times harder than the brake. It's not a good way to drive a car. It's not a very good way to drive a universe either. But if that's what's going on, then the universe will keep accelerating. If it's accelerating now, and dark energy is 3 times stronger than dark matter, then logically it will accelerate forever, and that's the eventual outcome. Now we can see that that must be the case because one of the attributes of dark energy is that it's quite a bizarre concept what dark energy is, given that we don't know physically what it is. It appears to have the attribute of being an emergent property or a function of the vacuum of space itself. And the nature of that dark energy is such that it doesn't vary with time. That's the simplest hypothesis for dark energy. However, the effect of dark matter on the universe does vary with time, because as the universe gets larger, the stuff in the universe, the normal stuff and the dark stuff, is being diluted in a larger and larger universe. So the decelerating effect of dark matter is declining as time goes by. So that really makes the projection that the universe will expand forever almost certain. Not only is the dark energy, which is accelerating it, 3 times stronger than the dark matter, as time goes by, the effect of the dark matter will decrease further due to the dilution of that gravitating material in a much larger universe. So really, taken together, cosmologists think it's almost certain that the universe will expand forever at an ever-increasing rate. The caveat, and it is an important caveat, was from the question last but one, about whether dark energy and dark matter vary with time, or how constant are they. If dark energy had the property somehow of decaying, and you might say, well, why would it decay? Well, the truth is we don't know enough about it to particles decay, even energy fields decay of other kinds. So we're not so confident that we understand dark energy to say that it might not decay over time. Well, if it decayed over time, then its accelerating impetus would decline, and maybe the dark matter would take over and the universe would reach a maximum size and recollapse. So that's possible. It's just possible. But based on what we know, we'll say the universe will expand forever at an ever-increasing rate. And so the universe essentially is just going to dissipate because that's an accelerating expansion. It's not actually, in the end, going to be a gradual thing. It'll be quite dramatic. In a few billion years, the thing will thin out vastly compared to what we see around us.
Julian has a question. If nothing moves faster than light, how do gravity and charge get out of a black hole? Meaning if photons and gravitons can't go fast enough to escape.
It's a great question. Right, so if the speed of light is a limit, how does a black hole even exert its influence? Julian has hit upon the flaw, if you like, one of the hidden flaws in the theory of gravity. So the standard theory of gravity, general relativity, makes a prediction that the force of gravity is carried at the speed of light, and that there's a particle that carries that force, a hypothetical particle with spin 2, as it turns out in the quantum theory, called a graviton. And there's a couple of problems with this. The first is that gravitons have never been observed. So of all the fundamental particles that are predicted by theory, graviton is one of the trickiest because Nobody's observed gravity in that way. Photons are observed like ways for the weak and strong interaction, gluons, which are very hard to observe in high energy physics experiments, but their existence has been strongly inferred, and people believe gluons exist. The graviton, really, there's no direct experimental evidence. So it's an unverified prediction of the theory. The other part of the theory that's unverified is the fact that the signal propagates at light speed. And that's a huge incompleteness in general relativity, if you like. Physicists have tried really for decades to design really clever experiments to somehow show that gravity propagates at the speed of light. They've used things like pulsars or compact stars that are changing their configuration to try and look for signal propagation effects that would indicate how fast gravity is operating through space and time. And those results just turn out to be ambiguous, or the experiments are just too difficult to conduct. So I'm afraid the simple answer to the question is, that's a conundrum, and actually maybe even a contradiction. The fact that we can't show the way gravity acts in that fundamental way, and of course that relates then to the properties of a black hole and how the gravity of a black hole is inferred. Stephen Hawking was honest about this in the 1970s. He said, because he realized black holes embody many of these issues or even contradictions, he said the postulation contains general relativity demise or incompleteness. He made a dramatic statement that a black hole contains the seeds of its own demise, where he meant the theory was incomplete. We already know that's true with black holes because black holes have a theoretical entity at the center which is called a singularity, which is infinite space density, and an infinite matter and matter density is a meaningless thing in physics, and so that's another reason the theory is incomplete. So nice one, Julian. You've hit on a problem in gravity physics. It's a fundamental one, actually.
Gabriella asks, if the universe is expanding, at the end, if there is an end, will we see a big freeze?
Well, I wouldn't want to be there. It's not going to be much fun, but a big freeze. So what does the end look like? Let's just play it out. Let's assume that what we measure now for dark energy and dark matter are the case, and that they would not, the dark energy in particular does not vary its intrinsic strength over time. So it just, what we see just plays out over a long future time frame. The universe will expand faster and faster. The Hubble expansion is an accelerating expansion. That leads to projection in something like of order 10 billion years, actually about similar time to the age the universe already been in existence, where the galaxies we comfortably see with our telescopes will be ripped from our view because they will move faster than light speed away from us. At the moment, we have to look pretty far away to see the horizon, or the limit of our view, the distance beyond which galaxies are moving away at the speed of light or greater, and so we don't get their light. We can't have their light, and it hasn't had time to reach us in 13.7 or 13.8 billion years. In the future, it'll be much more dramatic, because even galaxies that we comfortably observe with telescopes, galaxies a billion light years away or a few hundred million light years away, or the Virgo cluster, will no longer be visible, because that Virgo cluster will be moving away from us at faster than the speed of light. So these objects will move outside our horizon. So there's two fates to the universe, and I'll get to the sense of the question about freeze second. So the first consequence is the lack of being able to see stuff. The logical endpoint of this, and the number is a little uncertain, maybe 30, 50 billion years from now, is that there'll be nothing to observe. The Milky Way will have merged with the Andromeda Galaxy. That's fairly certain. The timescale for that is a few billion, 3 or 4 billion years. And those two galaxies will settle out. Maybe there'll be a nice, active, massive black hole there, so we'll get a nice light show. We'll have our own active galaxy. Finally, the sun will probably be unharmed through that interaction, but eventually will die. And so our universe will become one galaxy, the merged product of the Milky Way and Andromeda, dubbed Milkomeda by just had to come up. That's it. No extragalactic. I'm doing as much as I can while I have a career because, you know, there's no future in it, basically. The freeze part is interesting too. The universe is clearly going to keep getting colder. So now, 13.8 billion years after the Big Bang, the average temperature of almost every part of the universe, because almost every part of it is empty space, is just under 3 degrees Kelvin. 2.726, I think, is the exact number. And that will continue to diminish with size. In the simple thermodynamics of the expanding universe, the temperature is just an inverse relationship with age. Now that changes when it's accelerating, but basically the universe will just continue to get colder and colder and colder. And so that's the nature of the freeze. But of course, the universe is already very cold. I mean, it's 3 degrees Kelvin in most places. And the distinction between whether it's 3 degrees Kelvin or 1 or 10 Kelvin may be so interesting. So it'll freeze in that sense, but it'll also freeze in a second sense because the stars and all the galaxies will die, and there won't be enough material left for reignition of new stars. Basically, all the hydrogen will get used up. It'll either be used up and transformed into heavier elements, and or it will be trapped in stellar remnants, mostly by dwarfs, but also neutron stars and black holes, and therefore not able to participate in the formation of new stars. So another aspect of the great freeze ahead of us is the loss of stellar energy from nucleosynthesis. It just will not be possible. The last stars to die will be the lowest mass stars. Remember that down at the fusion sequence limit of 0.08 solar masses, 8% of the mass of the sun, the lifetimes are extraordinary. Lifetimes are hundreds of billions of years. So this freeze, this great freeze, or the deep chill over every galaxy will be complete essentially by 1 trillion years from now. Now we won't see this happen, assuming anyone's here to see anything, or some other aliens or our long descendants. We won't be able to see any of this play out in any of the other galaxies because they've already been lost from our view due to accelerating expansion. But we can be confident through the cosmological principle that the same thing is happening elsewhere in the universe, invisible to us, and that just as our galaxy is gradually turning dark and all the lights are going off and all the heat's going out of the system, that the same thing will be happening elsewhere. Really, it's quite a cheerful thought.
An inquiry from Bill. Has antimatter affected the rate of universal expansion by negating dark matter?
Negating dark matter. So, let me see how to answer that. I think in the analogy of an accelerator and a brake to the universe, dark matter and dark energy are sort of in a tension with each other. So, in a sense, it's dark energy that's negating the effect of dark matter, because as dark matter is trying to make things go into smaller and tighter configurations by gravity, dark energy is trying to do the opposite. But dark energy does not unravel the work of dark matter. So let's just view this as a titanic battle between dark matter and dark energy played out over the history of the universe. Dark energy looks like it will win. It will win. It's 3 times stronger, and if that's the case, it will continue to dominate, and accelerating expansion will continue. But dark matter, on the smaller scales than the entire universe, will win or dominate, because things will continue to clump on those scales. Basically, when a thing is held together by its own gravity, which is mostly dark matter gravity, it immunizes itself or decouples from the cosmic expansion of space-time. And so dark matter will keep winning these various little battles. It will lose the war. The war is what happens to the universe. Dark matter will not make the universe recollapse. But while losing the war, it's going to win an awful lot of little battles, because in these smaller regions, which could be the size of a galaxy or a cluster of galaxies or even a supercluster, dark matter will make the configuration become tighter and tighter, will drive things towards the center, and in fact will grow larger and larger black holes in the center of galaxies and so on. And that's really, a lot of that's driven by dark matter, because dark matter is governing the gravitational potential. So that's probably the best way to summarize it. The dark matter will continue to concentrate things on galaxy scale. Those scales is sailing faster and faster apart.
Errol wonders, you mentioned that simulations of the universe only work if dark matter is introduced in the equation, yet dark matter particles do not interact with other particles. Is this not a contradiction?
It's a good question. How do we put dark matter in a simulation? What do we assume? And it's important that we have to make an assumption. We don't, not knowing what the dark matter particle actually is, we have what we assume as an ingredient to a simulation clearly dictates the outcome. And really, for dark matter in a simulation, only two things are assumed, which really is the answer to the question. One is that the dark matter particle does not have electromagnetic interactions. In other words, it doesn't see radiation, care about radiation, scatter it, interact with it in any way. And that's fairly easy to do in a simulation, and that's what we to see in the universe itself. Because if dark matter had an interaction with the radiation that's abundant in the universe, we would have known that decades ago. So that's one property of dark matter, and the other property is just that it has gravity, because even if it's a tiny subatomic particle, we know that there are so many of those tiny subatomic particles that they rival the number of normal particles. Almost by definition, if dark matter is 6 times heavier overall than normal matter, those particles are extraordinarily abundant. Now, the individual particles themselves are more massive than protons and neutrons, and that's part of the nature of what people are looking for in the physics experiment. But they're extremely abundant, and so dark matter has a heft of gravity. So what you're doing in a simulation is you're putting in you're not really putting in a tiny particle at all. You're putting something into the simulation that has no interactions with light or any radiation, but exerts gravity with an inverse square law distance dependence. And you're putting in the right amount of it to account for observations of galaxies and clusters of galaxies. And that's all. Only those two things. You're assuming nothing else. But dark matter is immune from radiation simulations, but it has gravity. And so it has self-gravity. And since dark matter is the most dominant mass component of the universe, the gravitational interactions of dark matter with itself lead it to clump and form structures that we see typically as the halos of galaxies, within which the visible parts are embedded. And those structures grow over time. So dark matter halos, as they're called, have merged and got deeper over time. And we see that in a simulation, and part of the reason we believe dark matter exists is we see galaxies behaving as if they had dark matter halos with those properties. So that's, again, quite a long answer. But basically, very little is assumed about dark matter put into a simulation, only the things we think explain it in the real universe.
Okay, our next question is from Phil. He asks, why are globular clusters so old, and why have they accumulated around our galaxy?
It's a good question, because a lot of what we do in extragalactic astronomy is archaeology. The Milky Way is, we think, about 11 or 12 billion years old. It didn't actually form in the very first wave of galaxies in the universe, but it was around, early in the history. But it's changed a lot. It's grown, and to put together the history of the Milky Way is a really complex job, and a whole field of astronomy is devoted to sort of galactic archaeology of the Milky Way, and then there's all the other galaxies. The reason the globular clusters are interesting is because it's been known for 50 years or so, ever since we understood stellar evolution and had good spectra of stars in globular clusters, that these not all, but some of these clusters are extremely old. They're sort of primeval objects for the Milky Way. The ages are a little uncertain, but there are indeed globular clusters that appear to have ages of 10 or 11 billion years. And that's about as old as we think the entire galaxy is. So these were the first things at the scene of the formation. It's sort of like looking at the leftover material, cosmic dust, or leftover material from the formation of the solar system, the small rocky we talked about a few weeks ago. The debris from the formation of the solar system tell us about that earliest phase. So the globular clusters are just that thing for the galaxy, and that's what makes them extremely interesting. The fact that they do not share the particular nature of our galaxy, where there's a disk of stars and gas and spiral arms, but they appear to have an almost spherical distribution. Basically, the globular clusters measured instantaneously by radial velocity appear to orbit in a cloud, a sort of swarm, like an angry swarm of bees in a nearly spherical distribution, extending high above and below the plane of our galaxy. So the fact that they have that spatial distribution, nearly spherical, and the fact that they're the oldest things we can find in our galaxy is sort of telling us that the galaxy must have formed in a sort of spherical collapse way early on. And indeed, the theory of galaxy formation was informed by that awareness. And so we imagine that in their very first phases, galaxies form by almost spherical collapse. But because the clouds of diffuse material out of which they collapse tend to have a little bit of angular momentum, there is going to be rotation in that system. And as it collapses, by conserving angular momentum, the rotation speed will increase. The formation of the disk within our galaxy, where we live with the sun, which is the sun, of course, is a fairly recent member of the galaxy that was born 2/3 the way through the lifetime. So this disk, we think, formed subsequently. And the disk was gradually built up over time in a sort of inside-out manner, and took some billions of years to grow into the disk that we now inhabit. So the globular clusters are these nice tracers back to the earliest days of our galaxy, and a sign of how our galaxy formed, where a lot of the evidence of that formation process have been lost to us. When we look at an elliptical galaxy, we see a system that is almost spherical, and it is formed in this pure way, and for whatever reason never added a disk to it, and never developed the disk with spiral arms. Elliptical galaxies also have globular clusters, and people have observed globular clusters in the outer parts of elliptical galaxies and found again that they're essentially the oldest stars in those systems. So you can play the same game there. In most of the galaxies where you look, you can find globular clusters that seem to be the oldest stellar systems we can find, making them really useful tools to talk about how these things formed.
Okay, Alice Amanda was asking about multiverses. How many universes do you think there are?
Alice Amanda, I don't know why you need more universes. Is 100 billion galaxies is not enough for you? I mean, it's quite enough for me. You know, I can't even count them all, and I'm getting old and tired here. So, but you want more? That's fine. The multiverse theory, I think it's actually being kind to it to call it a theory. It's not a theory. It's a hypothesis. It's an idea. It's at the fringe of the subject, speculative. And in fact, material on this will come up next week. We're talking about galaxies this week. I'm not putting off the question. I'm just telling everyone that you'll see, I think, a lecture on this next week. But the basic idea is that we think when the universe was small and dense, the entire universe was once the size of an atom or smaller, and so it's logically consistent to talk about the universe, our universe, as a quantum event in its genesis. And if our universe was a quantum event, then whatever substrate reality led to our universe as a quantum event, it's plausible to hypothesize other quantum events. And this is out of something that we could barely even call a space-time, because it's a very physically unfamiliar situation. So the multiverse theory is rooted in quantum genesis of our universe, which is fairly conventional thought, given how the Big Bang was at its very earliest times. And then goes on to speculate that because of the nature of quantum processes, where they are physically random variables, that you would have physically randomly different properties of space-time seeds, or the quantum events, many of which are potentially occurring. And that, in a very small nutshell, is the multiverse idea. The most important question for people like me who are observers is, well, how can you test this idea? It sounds incredible, bizarre, crazy, speculative stuff. How could we test the existence of other universes? Well, and the answer is, at the moment, we can't. The theorists are understanding that they won't be taken seriously unless they can make a prediction that can be observed. And so they're working really hard on the theory, such as it is, to make a prediction that can be observed. And that's sort of where things stand. In answer to the question, which I think was the core of your question, of how many multiverses might there be, nobody has any idea, but the number is probably vast. Because if you just go right out on the tree limb to where it gets really thin and use string theory to try and calculate the number of possible quantum precursor states to the universe, it's just a ridiculous number. It's 10 to the power 100 or 10 to the power 500. Just a crazy number. So the answer, since Amanda K, since you're not happy with the universe with 100 billion galaxies, the answer is you can have as many multiverses as you want.
So the next question from Jerry is something that Carmen and I are wondering as well. It's that do globular clusters have black holes?
That's an interesting question that's controversial. It's a little subtopic that's very hot right now. The answer is maybe, but the reason why it's interesting is because, as we know so far in this course, nature makes black holes with a huge range of masses. In the early material on stars, we've seen that the traditional black holes are things maybe 3 up to 10 or 15 times the mass of the sun. That's a normal massive star dying and leaving a black hole. Now, in this part of the course, we're learning that not only does our galaxy have a 4 million solar mass black hole, but the most beefy active galactic nuclei can have black holes of billions of solar masses. I think the Guinness Book of Records number is 10 billion, roughly 10 billion solar masses. So nature makes black holes covering roughly a billion range in mass, and the punier galaxies have punier black holes. Our galaxy has a pretty modest black hole of 6 million times the mass of the sun. And a big question on the table for the last 10 or 15 years is, does nature fill in the dots? Does nature connect the dots and make black holes that are 100 times the mass of the sun, 1,000, 10,000, 100,000? And people have looked hard for that. And if you were hypothesizing a place where you might find, say, 1,000 or 10,000 solar mass black hole, it would be a globular cluster. If you could find globular clusters have a large concentration of mass, there's a very tight core, stellar core in globular cluster, and natural dynamical evolution could potentially lead to a black hole forming there. And it would grow probably slowly because there's not much gas in a globular cluster for a black hole to grow. The hole would have to grow by devouring stars whole, which turns out to be an inefficient process. So if you could form a black hole in a globular cluster, it wouldn't grow very rapidly, and it would probably stay small mass. And I would say in the last 7 or 8 years, there have been 4 or 5 claims of black holes in globular clusters, massive, 1,000 to 10,000 solar mass black holes. Most are controversial still. They usually use X-ray observations to try and decide that it's a black hole, because the black hole is not truly dark if there is some interaction with material. So the answer is, theoretically, we do expect the intermediate black holes to exist, and globular clusters are a great place to look. And the observational answer is not yet. They're not proven beyond doubt. But it may indeed be the case that nature makes every possible black hole size all the way up to 10 billion.
Okay, this next question will be our last question. It's from Julian. He asks, how big do you think the first population 3 stars were?
I'll give the overview of the terminology to Julian's question about POP3. Population 1 and 2 are traditionally traditional jargon of astronomers talking about stellar populations, old and young. POP3 was a designation reserved for the primordial stars of the universe, the very first generation of stars. The properties of POP3 stars are very interesting because since they're the first stars in the universe, there were no heavy elements. They were made just of hydrogen and helium in the same abundance that was given by the Big Bang nucleosynthesis from the first 3 minutes of the Big Bang. That's it, and a little lithium and deuterium. But basically, they are primordial material. So there's no carbon, nitrogen, oxygen because it hadn't been made yet. And when you go through the theory of stellar properties, that changes the properties of stars quite a lot. It changes their fusion rates and their equilibrium structures. The other thing to remember about population 3 stars is that they formed probably when the universe at a redshift of 30, say, and that means the universe was 30 times smaller and 30 cubed times denser. And so the theory of what population 3 stars are like is very interesting, and it's a little uncertain. It's hard to run those models. But the basic answer is that it seems likely in that physical situation to be able to have much more massive stars than we observe locally. The most massive stars that it's easy to measure, Nathan Smith, I'll refer to one of the podcasts, Nathan Smith, in my interview with him, talked about what are the most massive stars we measure. And he said that there's decent evidence for 200 solar mass stars, 150 solar mass stars, maybe more. POP3 stars could be even more massive still. Based on simulation and theory, they could be 1,000 times the mass of the sun. And of course, they'll live phenomenally short lives and detonate as incredibly energetic hypernova or supernovae and leave behind massive black holes, which we think will be the seeds for other black holes forming or black holes merging. Because remember, the universe is that much smaller and denser, so any black holes that you produce early on have a higher probability of running into each other and merging, which affects the growth rate of black holes. So Julian's question is a great one because it alludes to a whole set of issues that we'd love to know the answer to. How early were those first massive stars? How massive were they, since theory says they could be really massive, much more than we see in the local universe? What kind of black holes did they leave behind? And did those black holes actually form the seeds around which galaxies formed? In other words, the black holes sort of came before the galaxies. It's entirely plausible given what we know. Or was it the other way around? Now, answering those questions is really hard because redshift 30 is beyond any detection of a physical object so far. JWST will even be challenged to go back to that regime. But that's a nice question to end with. So thank you everyone for participating, and we'll be back. We'll vary the time and day just to keep it possible for as many people's schedule as possible. And keep asking questions online. I'm happy to answer those. And I'll see you all next week.